Chapter 5 Molecules and Compounds. Sugar and salt, two white crystalline substances we know well. They are compounds. A sucrose molecule, shown here, contains carbon, oxygen, and hydrogen, all in a specific arrangement of atoms. This is a molecule of sucrose. The properties of sucrose are very different from those of carbon, which is carbon alone in graphite, shown here. So the arrangement of atoms into molecules determines what the substance is like, its properties. For instance, sugar and salt. Here's an example of sodium, and here's an example of chlorine. And when they combine together, they form a white crystalline substance called sodium chloride or salt. Sodium chloride, this compound formed by sodium and chlorine, has properties very different from the elements that make them up. Compounds display constant composition. Most of the substances we encounter are not elements, they're compounds. And a compound is a different kind from a mixture. It's a pure substance. In a compound, the elements combine in fixed, definite proportions, whereas in a mixture, they have any proportions. Let's looking at compounds showing constant composition. A mixture, balloon is filled with a mixture of hydrogen and oxygen, so you can have any amount of hydrogen and oxygen. It can vary. Whereas a chemical compound, such as water, here's a balloon filled with water, it is made up of an amount of oxygen and hydrogen to form the water molecules, always 2 atoms of hydrogen to 1 atom of oxygen. It was Joseph Proust who stated the idea that elements combined in fixed proportions to form compounds. It's known as the law of constant composition. All samples of a given compound have the same proportion of their constituent elements, no matter where you found the compound. Water in Australia is the same as water in Canada. Constant composition. We can express this as a mass ratio. For example, we decompose 18 grams of water, we should get 16 grams of oxygen and 2 grams of hydrogen. It's in a mass ratio of 16 to 2 or 8 to 1. This is true of any sample of pure water. Its mass ratio is constant, the same. If we decompose 17 grams of ammonia, which is composed only of nitrogen and hydrogen, we get 14 grams of nitrogen and 3 grams of hydrogen in a ratio of 14 to 3 or a 4.7 to 1 ratio. Even though atoms combine in whole number ratios, their mass ratios are not necessarily whole numbers. Chemical formulas, how do we use them to represent compounds? Compounds have constant composition with respect to mass because they are composed of atoms in fixed ratios. A chemical formula indicates the elements present in a compound and the relative number of atoms of each. For example, H2O is a chemical formula for water. It indicates that water consists of hydrogen and oxygen atoms in 2 to 1 ratio. Notice that the subscript 1 is normally omitted. More about how to represent compounds. Table salt is NaCl, indicating 1 sodium atom and 1 chlorine atom in a 1 to 1 ratio. Carbon dioxide has carbon in a 1 to 2 oxygen ratio. Table sugar has carbon, hydrogen, oxygen in a ratio of 12 to 22 to 11. The subscripts in a chemical formula represent the relative numbers of each type of atom in a chemical compound. They never change for a given compound. What is the correct order of elements in a compound? Well, chemical formulas list the most metallic elements first. For instance, sodium chloride is Na and Cl, not Cl then Na, because sodium is a metal and chlorine is a nonmetal. In compounds that do not include a metal, the more metallic-like elements listed first. For instance, nitrogen dioxide would have the nitrogen first, followed by O2, or nitrogen monoxide, not the other way around with the oxygens first. Within a single column of the periodic table toward the bottom, they're more metallic than those on the top. So we'll write sulfur first and then oxygen, SO2, not the other way around. How to represent compounds with polyatomic ions. Some chemical formulas contain groups of atoms that act like a unit. This makes it easier. When several groups of the same kind are present, their formula is set off by parentheses and a subscript to indicate the number of that group. Many of the groups of atoms have a charge associated with them, and so they are called polyatomic ions. To determine the number of each type of atom in a compound containing a group within the parentheses, you have to multiply the subscript outside the parentheses by the subscripts for each atom inside the parentheses. For example, magnesium nitrate. Here's its formula. From the formula, it indicates a compound containing 1 magnesium and 2 nitrate groups. The NO3 is a group. So outside of the group, we see the subscript 2. Inside, we see this subscript on oxygen 3. So to calculate the number of atoms, we say then that there's 1 magnesium, there's 1 nitrogen inside, multiplied by the 2, so there are 2 nitrogens, and 3 oxygens inside multiplied by the 2 gives us 6 oxygens. This is the total of the atoms in this group, in this compound. We have many different kinds of formulas. One called the empirical formula, it just gives the relative number of each element in a compound, not the actual. And then we have the molecular formula, which gives the actual number of atoms of each element in a compound. For example, hydrogen peroxide is H2O2. That's its molecular formula. But its empirical formula is HO, because it's 1 to 1. The molecular formula is always a whole number multiple of the empirical formula. So you see, if you take the empirical formula here and multiply it by 2, you get the molecular formula. A structural formula is sometimes used in chemistry also, but we're not dealing with that right now. So from many types of chemicals, we have molecular models, and these are three-dimensional representations. We have ball and stick models, we have space-filling models, and many times we just represent the atoms of different elements by a specific color sphere. Here's a comparison of the difference. This is the molecular formula for methane, CH4. And it's a structural formula, shows you how that all 4 of the hydrogens are hooked to the carbon. This is a ball and stick model with the carbon in the middle and the hydrogens in that shape, the tetrahedron shape. And then this is a space-filled model. Image makes a connection between the world around us and the world of atoms and molecules. Macroscopic view is what we see in a glass of water. The molecular or microscopic, submicroscopic really view then would see the atoms. Pure substances may be either elements or compounds. Elements may be either atomic or molecular, and compounds may be either molecular or ionic. Here's a general classification. Pure substances. They're either elements or compounds, but the compounds could be of the molecular type, that's like water, or it could be the ionic type, like sodium chloride. And elements then can be atomic, for instance like neon, or molecular, bimolecular O2, two oxygen together to form oxygen. Atomic elements are those that exist in as single atoms. Molecular elements are those that normally are combined. Very often these are diatomic elements, two atoms that are bonded together, and that's their basic unit. Here's a picture of mercury, which is a single atoms of mercury. On the other end, here's chlorine, which is a diatomic element. This table is important to know if you're not sure whether it should be represented as a diatomic. So these are the elements, mostly gases, and the halogens. Hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine should all be diatomic, subscript 2 in their basic unit. Molecular compounds are formed from two or more nonmetals. Ionic compounds always contain one or more cations, metallic, and one or more anions, which are nonmetals. Compounds may be molecular or ionic. Again, we showed the example of dry ice. It's a compound made up of molecules. The sodium chloride is an ionic compound, in which is arranged in a crystal lattice. When a metal, which has tendency to lose electrons, combines with a nonmetal, which tends to gain electrons, we can form ions. A compound composed of a metal and a nonmetal is considered ionic. The base units of ionic compounds are the formula unit, since they aren't actually molecules. Unlike molecular compounds, ionic compounds do not contain individual molecules, but rather cations and anions in an alternating three-dimensional array, a lattice. Let's review. We want to be able to write formulas for ionic compounds. So we have to understand which elements form ions with a predictable charge, and which ionic compounds always contain a positive and negative ion. And in the chemical formula, the sum of the charges of the positive ion, the cations, positive cations, must always equal the sum of the charges of the negative ions, anions. So we write the symbol of the metal and its charge, followed by the symbol of the nonmetal and its charge. Then we make the magnitude of each charge on each ion without the sign become the subscript for the other ion. If possible, reduce the subscripts to give the ratio of the smallest whole number, and check and make sure the sums of the charges of the cations equal and cancel the sums of the charges of the anions. Here's an example. We want you to write the formula for the compound between aluminum, a metal, and oxygen, a nonmetal. So looking at the periodic chart, we see the aluminum is in group 3, therefore the metal tends to become a 3+. And the oxygen is a nonmetal, becomes a 2-. So what we see that if we put the subscript 2 behind the aluminum and the subscript 3 behind the oxygen, we get a neutral compound, the correct formula. Because 2 times 3 is +6, and 3 times 2 is -6, +6, -6, neutral. We can see for magnesium oxide, Mg is +2, it's in group 2, and oxygen -2. They changing the subscripts, we get Mg2O2, but we should reduce that to MgO because these to the smallest ratio. Naming compounds. We have a nice system for naming compounds, and if you learn the naming rules, you can examine a compound's formula and determine its name, or vice versa. Many compounds have a common name. H2O has a common name of water, but its systematic name would be dihydrogen monoxide. Since water is a familiar compound, everyone calls it water, not its systematic name. Common names can be learned only through familiarity. There is no system. First step in naming an ionic compound is identifying it as one. Make sure it's an ionic compound. And that would mean that you have to have a metal with a nonmetal. Then you assume that it's ionic. Ionic compounds, you have a metal and a nonmetal, and the metal forms only one type of ion, or the metal forms more than one type of ion. So you have to look at the metal to decide which type it is, type 1 or type 2. First type, type 1, contains a metal with no possible change. All of those representative elements, for instance, in group 1A, they all like to be +1. Group 2A, they like to be +2. They don't change. The second type is called type 2, and it changes. It can have a different charge. Many of the transition metals, although not all, are like this. And some of the main group elements, especially the heavier ones down toward the bottom, like lead and tin, they can have more than one type of cation. Here's a list, and this is found in your book, of table 5.2 of the metals that only have one ion. This is all type 1. All of those in group 1 are +1. All of those in group 2 are +2. Aluminum is +3. And zinc and silver are transition elements with just one charge. A +2 for zinc and a +1 for silver. Now here are some metals that form more than one type of ion. We have chromium. It can be a +2 or it can be a +3. So we call the +2 chromium, Roman numeral 2, chromium, Roman numeral 3. Iron is another one. Has +2, +3, iron 2 or iron 3, etc. Always refer to this table to make sure you know the charge of the cation for a compound made with metals type 2. Binary compounds, they have two elements present. In the case of binary ionic, they're going to have a metal, cation, the positive part, and a non-metal anion. So all you have to do is name the metal cation, and then for the base, take the base name of the anion and change its ending to "ide," I-D-E, ide. It will always mean it's a binary compound, only two elements present. Here's an example. Sodium chloride. The metal is called sodium. You just name it. And then you see you have chlorine, and so we trunk off the ion and put on the ide. So the full name of this is sodium chloride. Here are the base names of some nonmetals and how you adjust them to be the ide ending. Fluorine becomes fluoride. Chlorine becomes chloride. Bromine becomes bromide. Iodine becomes iodide. Oxygen becomes oxide. Sulfur becomes sulfide. And nitrogen becomes nitride. Since the charge of the metal cation is always in this type of ion, we have to be concerned about the metal cation that would have different charges to it. So in the name we have to specify what the charge of the metal ion for those that vary, type 2. And we specify this with a Roman numeral. In case you've forgotten your Roman numerals, number 1 is just this I, 2 is 3, 4 IV, etc. For example, copper has more than one possible charge. It's found on that table. It can be copper +1 or copper 2+. So we have to distinguish them. So the +1 will be copper Roman numeral 1. Notice there's no space, it's just parentheses Roman numeral 1. Copper parentheses Roman numeral 2. So if there's more than one kind of cation, you have to name the metal, put the charge of the cation in Roman numerals, and then add the base name of the anion, the nonmetal, changing it to "-ide". What if you don't know the charge but have the form of a metal with various charges and you have the chemical formula? Well, remember this: the sum of all the charge must be 0 in a formula. So if we're given a formula iron Fe, chlorine 3, then we figure that the iron must have the +3 charge in order it to be neutral with 3 -1 chloride ions. So this would be iron Roman numeral 3 chloride. Again, I show you the name. It's iron 3 chloride. How do you name ionic compounds that have a polyatomic ion? Well, some ionic compounds have these polyatomics, and they are composed of a group of atoms that stay together. Ionic compounds contain polyatomics are named using the same procedure as we apply to other ionic compounds, except we use the name of the polyatomic ion whenever it occurs, rather than putting that ending "-ide" on. Here's a list of some common polyatomic ions, and you might, that's table 5-6. You might want to refer to it when you're doing your quizzes and help you in your homework. We have acetate, C2H3, it's a -1. We have carbonate, and so on. These are the various names and charges of the groups that stay together. Chromate, dichromate, phosphate, hydrogen phosphate, ammonium. It's the only positive cation polyatomic. Then we have hypochlorite, chlorate. Okay. Well, more about how those are named, but this table could be used as a reference to help you. Most polyatomic ions are oxyanions. That is, they contain oxygen. So when a series of oxyanions contain different number of oxygens, they are named systematically according to the number of oxygen atoms. For instance, NO3 has 3 oxygen atoms, say -1 charge. It's called nitrate. There is a polyatomic NO2, dropping 1 oxygen, still the same charge, and it becomes nitrite. The same way with sulfate, SO4 -2, sulfate. SO3, dropping 1 oxygen, still -2, sulfite. Here's a kind of list of those different compounds. Hypochlorite. If you start down here, you have the perchlorite, 1 more, then you have the chlorite, and hypochlorite. These 2 in the middle are familiar. This is even 1 less oxygen. This is even 1 more, per. The halogens have these prefixes hypo and per to take care of 4 different polyatomic anions they form. So we have lots of polyatomic anions in everyday chemistry. We got sodium hypochlorite, which is bleach, a component of bleach, or baking soda is sodium bicarbonate, or calcium carbonate is in antacids. Sodium nitrite is a food additive to preserve packing meats. Now, how do we name molecular compounds? These are not ionic compounds, so they are going to be molecular, and they'll be between nonmetals. There'll be no metal present. So we simply put a prefix and the name of the first element, then another prefix, and the name of the base element changed to "-ide" because they're binary. Some examples. What are the prefixes? Well, they simply tell you the number. Mono means 1, di means 2, tri 3, tetra 4, pentra 5, hexa 6, hepta 7, octa 8, nona 9, and deca 10. How does this work? Well, we see this is CO2. Normally, the first element, if it's 1, we skip the mono. So this becomes carbon, one of those, di, ox, change it, oxygen to oxide. This is carbon dioxide. N2O, very easy. It's dinitrogen monoxide. And then we had to make a little change here. Since mono and oxide both, we don't repeat the O, so it's just monoxide. It's not monooxide. So dinitrogen monoxide. But it's not always the same. For instance, with chains of triiodide, we leave the tri and the iodide. So different in some cases. Naming acids. This is the last bit of nomenclature. Acids are molecular compounds that form ions when dissolved in water. And more specifically, they are composed of hydrogen, which becomes a hydrogen ion to make it an acid. And usually the hydrogen is written first in the formula and then followed by one or more nonmetals written second. We have acids that are binary acids, that's hydrogen and some nonmetal, or they're oxyacids, that's hydrogens and some polyatomic anion containing oxygen. How do we classify acids? Acids, their formula has hydrogen as its first element, and it be binary, contains 2 elements, hydrogen and a nonmetal, contains hydrogen and a polyatomic anion with oxygen. If they're binary, the name is easy. We simply put the word hydro in front, name the metal, the nonmetal that it's being made up of, and add "ic" to the end. Example will help. This is binary, 2 elements, hydrogen, chlorine, and so it is hydrochloric acid. Binary, hydrobromic acid. Okay. How would you give the name of this one? Hydrogen and sulfur. Well, it's hydro, because it's binary, then sulfuric acid, hydrosulfuric acid. Some acids are oxyacids, and they have to be, you have to refer to the table of polyatomic anions to decide how to name them. They only contain, you just simply name the polyatomic anion and add the suffix on it, depending whether it's nitrate. This is nitrate, and this is sulfite, and this is sulfate. So these will be a combination of hydrogen with the oxyanion. Let's name them. The oxyacids, they contain oxygen. So the name of "ite" for the oxyanion, or we have "ate" for the oxyanion. It works this way. The names of acid containing oxide ions are simply, if they end in "ite", then you replace the "ite" with "ous" and then add the word acid. Here's the sulfite polyatomic anion, so this is sulfurous acid. Please note that you don't begin with hydro. This is nitrate, so it becomes nitric acid. This is sulfate, so it becomes sulfuric acid. Sulfite, so it becomes sulfurous acid. Here's a table that you can refer to in your book for the names of these oxyacids. Here is a flow diagram that will help you in naming the compounds. If you decide you have an ionic compound that is one between a metal and a nonmetal, then you look at the metal. Does it form one type of ion, for instance in group 1, A, 2A, or does it form more than one type of ion, such as in the transition elements, or you can look on the table. If it's only one type, you just name the metal and then put on the base name of the anion, the nonmetal, and change its ending to "-ide". If it's more than one kind of metal, then you have to put down the metal and Roman numerals indicating the charge, and then followed by the nonmetal base with the ending "-ide". If they're molecular and that's only nonmetals, then you just simply give the name of the prefix, name of the first element, prefix, name of the second element, and change the base ending of the second element to "-ide". For acids, they're either going to be binary, 2 elements, in which case they'll begin with the word hydro, the base name of the nonmetal followed by "-ic", or they'll be oxygen-containing things, of which you'll have to look up the name of the polyatomic anion if it's 8 or "-ide". If it's "-ide", change the base name of the nonmetal, the polyatomic, and to "-us". If it's 8, then change the base name of the polyatomic anion to "-ic". This is just a little quick review. We begin looking here and we identify that as 2 nonmetals. So we follow the molecular flow chart and we know it's 1 and 1. We say carbon, we can skip the mono on the first element, and monoxide. This is metal, calcium and fluorine. So it's an ionic compound. Calcium is only 1 valence in group 2A, a +2, and so is calcium fluoride. This is a binary acid, so it must begin with hydro and name this fluoric. Here's an ionic compound, a metal with a non-metal polyatomic. The polyatomic's charge nitrate is -1, and 3 of them make a -3, so this iron must be using its +3 valence. So we'll have to put a Roman numeral 3. This is a oxyacid, so we'll just name it after this. This is the perchlorate anion. You may have to look that up. So this is perchloric acid. Again, this is sulfite, and so is sulfurous acid. Finally, the last important thing is we got to be able to get the formula mass of a molecule or a formula unit. It's basically very simple. All we have to do is get the sum of all the atomic masses found on the periodic table. So we just simply calculate this, the number of atoms of each element in the chemical formula times the atomic mass of the first element. Go ahead, the next element, keep summing these up till you get the total formula mass of, or from a formula unit or the molecular formula. So many skills required in this chapter, but none of them too difficult. We must know that how to write chemical formulas. We know how to find the total number of each atom in a chemical formula. We must be able to classify elements as atomic or molecular, usually bimolecular. We classify compounds as ionic, metal plus nonmetal, or molecular, nonmetals. We must be able to write the formulas for ionic compounds, balancing their charges. The cation's positive with the anion's negative. We must be able to name binary ionic compounds that contain a metal that has only one type of ion, and the binary ionic compounds containing a metal that has more than one type of ion. You'll have the Roman numerals here. We must have name compounds that have polyatomic ions. You have to look up the polyatomic ion's name. It'll be 8 or 8. We must name molecular compounds, which are simply nonmetals, by putting the prefixes. Binary acids, they always begin with hydro. Oxyacids, we have to look at the name of the polyatomic anion. If it's 8, then the acid will end in ic. If it's ite, the acid will end in us. And we have to be able to calculate the formula mass of compounds given the formula.